I've been building up this low poly terrain example for a little bit now, which I can zoom out a little bit and you can see what's going on here. So today what I'm going to do is talk a little bit about this example, and then we're going to build up probably just the mesh and the vertice deformation today. In the background, you can see here we have an environment map, a skybox, whatever you want to call it. And then we also have pools of water with a shader on them. You can see that the environment map is kind of reflecting off that water, but we can also kind of see the depth in there. We got a little bit of bloom on the top of this mountain on the right-hand side, and otherwise this is just a very regular, very basically put together low poly terrain built out of noise procedurally inside of the Bevy game engine. If we take a look at the wireframe here, you can see a little bit about how many polygons there actually are in this, and also that they are very regularly spaced. That's because we aren't actually generating any fancy algorithm. We're not building our own mesh here. We're going to take just a plane, apply some noise to it, get some colors and some height differences out of the other end. And then in the future, I'll probably do a different video on environment maps and a different video on this little water effect shader that we have going on here. It's a little bit hard to see in the current incarnation, but there is actually animated water here, which is just a second plane in the same vein as the first plane that does the landscape. The other thing I'll mention before we really get into this is if you're really into procedural landscape generation, if you really want to do some more complicated algorithms, there's absolutely software out there. This is gaea, G-A-E-A, from Quad Spinner, and it can do a whole bunch of different things, a whole bunch of fancy algorithms, but fundamentally, you're still taking a plane and modifying the mesh, etc. So let's get started here. I'm going to do cargo new with the name of my project. We'll open a VS Code editor here, and we're going to need 3 dependencies. One of them is going to be Bevy, so that'll be cargo add Bevy. We're also going to use the noise crate, so I'll add that as well. And then a crate called Bevy pan orbit camera to have that camera that I was using to kind of navigate around and take a look in more depth at the landscape. So to start out, we'll need to bring in the Bevy prelude and start an app. We'll do app new, add plugins, and then we'll just boot up a new app, add the default plugins and run it. This will get compiling on the left. And in the meantime, we'll take a look at the dependencies on screen so that you can see which dependencies I'm actually using. We're in 0.14.2 for Bevy right now. In future videos, we'll probably move to 0.15, which would be the main branch currently, but we'll talk about why then. Bevy pan orbit camera, again, is just a camera plugin that we're going to use to be able to kind of move around and see the plane in different perspectives. And then noise is going to be noise generation for us, which we'll talk about in a second. So we've got Bevy installed and our application is running. So we'll start off here with just a camera. This is placed in kind of an arbitrary location, but you can see because our screen is no longer black, it's kind of this gray color, that the camera is active in the scene. The transform position here doesn't really matter. We're using looking at to look at x0, y1, z0, which is basically the origin, but slightly above the center point with a y-axis of, y. And our next goal is to get an actual plane into the scene. So the easiest way to find the most up-to-date way to do that is to actually check out the Bevy examples. This happens to be the 3D shapes example. And if we look for plane 3D inside of it, we can see that we get this PBR bundle, which is exactly what we're looking for. So if you're ever, for some reason, confused about how to spawn a specific kind of 3D or 2D object, those examples are always there. And then we'll also want some of these arguments for this setup function as well. In our case, we don't have images, so we only need meshes and materials. This is the assets database in a resource for meshes so that we can create our plane 3D and add it. And this is the standard materials. So since we're spawning a PBR bundle in here, that will be a standard material. We'll add that standard material or a handle to that standard material. And then here, I'm actually going to do color white instead of color silver. And we end up with this plane. But we did say it was white, and we can't move the camera yet. So it looks gray, even though we said it was white. And if we spawn in a directional light, we can kind of see that that's because of the amount of light in the scene. So that was an overcast day. There are a number of constants that we can use. For example, full daylight gives a much truer representation of that white color that we expected to see in this plane, but I'm going to leave it back at overcast for now. The other thing I want to do before we move on is make it so that our camera can move around a little bit. So we're going to bring in pan orbit camera plugin from Bevy pan orbit camera. That's the dependency we added earlier. And we can put the pan orbit camera default settings onto our camera 3D bundle, which then allows us to start zooming in, zooming out, looking around a little bit and whatnot. Now you'll see if I go underneath this plane, it actually disappears. And that's because planes like this, or any triangles have a front face and a back face, and we're only rendering the front face here. So we're what's called culling the back face. So if we're looking at the back of this plane, we won't see anything. So keep that in mind if you've set up your camera in some sort of funky configuration, especially something that is negative on the y-axis. The other thing that will be interesting for us is actually going to be the wireframe. So because we're planning on actually modifying the vertices in this plane to create our landscape, we can go over to the wireframe 3D example. And the things we need to set up here are the wireframe plugin with some additional WGPU settings. I'm not really going to cover exactly what these are because they're just kind of things you need to make wireframes work. They're not things you need for low poly landscapes. But with the render plugin in and all of the different sub features brought into scope, including the wireframe plugin, I'll then write a really quick function, which I actually have already written, and one new component. So in this case, we're going to use a terrain component to identify our landscape. We're going to pull in the wireframe component from the wireframes support inside of Bevy. This toggle wireframe function is going to query for landscapes that have terrain and have a wireframe, as well as landscapes that have terrain and don't have a wireframe, which gives us the ability to check keycode input, in this case keycode space, and then flip them one way or the other. This is just a really quick way to get in toggleable wireframes for this plane that we're going to be working with. So on this PBR bundle, we are going to want to add our terrain component because that's how we label what we want to put the wireframes on there. And then up in our app, we'll do an add systems. There's an S on the end here in the update schedule, and we'll run toggle wireframe. There are run conditions. We could run this only when we hit the spacebar, but that's not really the point today. All we want out of this is something where we can hit spacebar and see all of these lines show up, and then hit spacebar and then see them go away again. So from looking at this, you can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, if I just counted correctly, boxes. So this is 11 by 11. You can see that the plane is already divided into triangles, which is pretty typical. So what we are going to do is raise the points of each of these vertices using a noise algorithm of our choice. It's going to be whatever we want. And that will deform this plane into looking like terrain. And you can see in our plane settings, we've got a plane 3D default with the mesh. It's got a size of 50 by 50 and 10 subdivisions. If we bump this down to 1 subdivision, note that we are talking about the number of subdivisions, not the number of quads or triangles or whatever you want to say. So 1 subdivision will give us a 2 by 2 or 2 by 2 plane instead of 1 big. And this is a number both for the size of the plane and the number of subdivisions that you can just play with and do whatever you want. Now, the big question is, how do we actually do that, right? We need some way to access the vertices on this plane. We need to modify those vertices to be some arbitrary height based on some algorithm that we write. And in our case, we're going to start out, we're just going to call this terrain, and right above where we're spawning it, we're going to say let mute terrain equals this plane 3D. This does give us a plane mesh builder, which is not really what we want. We do want the actual mesh here because once we've built it, we want to access these vertices, and the mesh will contain that vertex data. So obviously I've already written this example and I've done this before, so I already know what exists here. But if you go to mesh, the associated constants are going to be really interesting for us. In this case, we're going to look at attribute position, which is where a vertex is located in space. And it says something here about the format of the attribute being vertex format float 32 by 3. This is basically a vec3 of F32s. If you click on this, it'll tell you exactly that. It's a vec3 of F32s. So that's the XYZ position of each vertice. And there's a couple of extra functions here. If we were, say, building up a custom mesh from scratch, it looks like there's an example that uses this on line 107. So from line list for mesh, this is custom mesh creation from a line list, and it creates a new mesh and then inserts some attribute positions. Now that would work if we wanted to do something a little bit more intense, but we already have positions. And there's these additional functions on mesh called attribute and attribute mute. So if we click into that example, we can see, hey, there's a mesh here. We use attribute mute, in this case, to get the UV channel or the UVs in channel 0. And then it destructures that float 32, so that vec3 that we saw earlier, iterates over them and changes them a little bit. This is basically the same thing that we're going to want to do. So let's start off by copying some of that code in. We need Bevy render mesh vertex attribute values so that we can get the destructure of this float 32 by 3. So we do our terrain, which is our mesh, dot attribute mute, and we're grabbing the attribute position that we saw earlier from that const, and this will destructure into giving us positions. Positions will be a vec of arrays of length 3. So now this shouldn't have adjusted any of our actual program running already. So we can run the program, close it back out, and take a look at where all these vertices are. Probably easier if we don't have as many vertices. So if I chunk my subdivisions down to 1, then it becomes a little bit more obvious where the vertices are being placed because they'll be almost exactly halfway. We've got size of 50, so -25, 0, -25, and so on and so forth. Each of these is a vertex location. So that really saves us from needing to like pair everything up or figure out where things are or construct our own mesh here. So if we iterate over positions, in this case with iter mute, we're going to get a mutable reference to this XYZ array. So if we want to, we could do something like pos1 equals pos0 plus pos2. And what this is doing is setting the Y axis to the X axis plus the Z axis. So if we start the program, we don't see a mesh here, but keep in mind that's why we had this camera around, because we do need to actually view the front side, and you can see that it's actually been deformed in this huge slant. And you can absolutely put whatever kinds of values in you want here. So in this case, we've got X plus Z, and we're taking the sine of that, which is -1 to 1, so you can start to see, you know, these kind of sine waves in the landscape. If we only do one of the axes, so let's say the x-axis, and we bump the subdivisions up to 1,000, you can start to see a very clear sine wave showing up in this terrain. It's a little bit awkward to look at because it is actually just a plane, so if you look directly on the side, you'll actually not see anything, but this is all fine for us. So what do we do next? Now we can deform these vertex positions by grabbing the positions out of the mesh using this attribute. We can modify them. How do we want to modify them? And my go-to for this is usually the noise RS crate if I'm going to do noise in Rust. Noise RS, as you can see here, allows you to construct some new Perlin noise with a seed. In this case, the seed is 1, and then get some 3D Perlin noise in this case. So there's an X, Y, and Z value, and the value here comes out as -1 to 1. There are all kinds of different noise. Perlin and simplex are some of the more common, but there's also Worley and some other combinations of different noise as well. So we can start off with this. So we'll take the imports and we'll bring them all the way up to the top. That's noise function, Perlin, and seedable in this case. And in this case, the value is hard-coded. So you can run your application with this debug for that value to make sure that it's working at all. In this case, it's doing -0.6 whatever. And if you ever do this and you want to use only 2 factors, but you run into something maybe a little bit like this, where it says the trait isn't implemented, and it says, okay, the trait is implemented for F64, 1, 2, 3, and 4. So it looks like we actually do get one of these 4 dimensions, but we're using an F32 here, so we will want to bump that up in this case. So now we have X as an F64 and Z, both going into the Perlin noise, and that gives us a whole bunch of different values. So let's drop that in here. This will want to go back to an F32. Luckily, the output of Perlin noise is well defined from -1 to 1, so we don't actually have to worry about this. We're not losing any precision here. And now we have this huge, very noisy plane. If we zoom in a little bit, we can see a whole bunch of different mountains and different places and different heights. And this is basically how we're going to create our terrain. Now we said this is going to be low poly, so maybe we do something more like 100. And you can start to see some of the polygons come through here. But we also don't want this to be as intense as it is. So what we can actually do is divide it by whatever we want, and this will kind of slow it down, so to speak. You can imagine if you have a number, and we're using like X and Y as input, right? And it goes from 0 to like 25 in this case. If you divide this by something like 10, you have to go through much more of the range to get the full amount of values. So we're kind of cutting that down and making it smooth out a little bit more. In this case, it looks like 300 is a little bit too much. So let's start off with something much smaller. Something like 20 starts to give us something that is still very, very smooth. Let's drop it down even more. Still feels a bit too noisy for my liking. And this is going to kind of be a matter of taste kind of thing, but it's also going to be relevant for the size. So let's bump this way up. We'll do 1,000 by 1,000 instead of 50 by 50. And now the impact of the noise is also going to be a little bit different here. Now, one of the things that is an issue for us right now is that these numbers are -1 to 1. We don't really want that as our range, right? So if we want, say, our highest peaks to be 10 and our lowest peaks to be 10, we can do this with Perlin noise by multiplying the output value, which is -1 to 1, by 10. And then we get a little bit more than we had before in terms of variation. So you can kind of just play with these numbers however you want. In my case, I feel like I can't really get a good grasp of what this is actually going to look like without it being colored, right? It's kind of just gray right now. It doesn't really show me anything. It kind of looks single colored, if you will. And one of the reasons, if we look at the difference between what it looks like now with what it just looked like, is that when we look at the lighting for this plane that we've deformed, so we've moved all these vertices, but the normals haven't changed. So we've kind of modified the locations of all of these vertices, but we haven't changed any of the normals. And the normals are really important for lighting. So when we compute the normals, you can see this get a lot more interesting. Whereas if I take the normals back out and run the application again, on the right-hand side, we haven't recomputed the normals, so they're still looking like they're a plane, right? Just a regular old plane. Whereas on the left, those normals have been recomputed so that it represents the actual structure of our mesh, and thus the light hitting it can put shadow in the right places. So one thing you're definitely going to want to do after modifying these positions is to compute the normals so that you can actually get something to look at. Now you can play around with these numbers, the size, the subdivision count, the sort of speed of the noise, if you will, as well as the terrain height to find something that you might like or not like. And don't worry, that is always going to be modifiable in the future. So I'm going to start with a terrain height of 70. I'm going to label that specifically. I'm going to set my subdivisions to something more like 200 with a size of 1000 by 1000. When we get into these positions then, I'm going to divide this by 300 and multiply by the terrain height, again computing the normals at the end. And that gives me something a little bit more like this, a little bit more up and downy, a little bit more like mountainous, if you will. But I still think there's kind of an issue here, and that's that we're only using one instance of Perlin noise, which makes this very, very, very smooth. You kind of have like one peak here, and then it goes down into one valley. When realistically, terrain is going to have a lot more variation on this slope. It's not going to be a perfect slope. So the other change that I'm going to make here is instead of using Perlin, I'm going to put this back up with our other stuff, and I'm going to use basic multi with Perlin. And then this noise is going to be our noise.get instead of Perlin.get. And I didn't bring that into scope, so I'll do that right at the top. And now immediately you can see something that looks a little bit more landscapey, a little bit more terrainy. It has a little bit more variation in the slopes that we were seeing. So you've got these deep valleys that have their own little bits of noise in them. And that's because, we can zoom out here to see what this actually looks like. And that's because Perlin noise only gives us effectively one octave is what it's called. But basic multi will give us multiple octaves alongside a couple of other variables that we're not really going to talk about. If you're familiar with like the Fourier transform or something like that, in the same way that many sine waves can make up a single audio signal, we can have many octaves of Perlin noise operating at different levels, which as a broad stroke means that we can define the peaks and valleys, the biggest differentiation by one octave of Perlin noise. And then on top of that octave, we can layer another one, which changes, maybe half of what the original did. And then another one that changes maybe half of the height that the second one did. And another one that changes half the height of that one. And we can do this as many times as we want. And you end up with this, like, instead of those very smooth peaks that we saw before, you get that smooth peak, but you also get that additional smaller effect noise layered on top of it. And it ends up looking very, very, very much more terrainy, in my opinion. So there's all different kinds of noise. You can combine them in all different kinds of ways. This is just one way. But this is still very gray and uninspiring. So let's get to coloring it. So right inside of our positions block here, when we destructure these positions out, we're doing a bunch of modification of these vertex values. Right below that, what we'll do is we'll set up colors, which is going to be a vec4, that's RGBA, red, green, blue, and alpha. We're going to take those positions that we just mutated, iterate over them, and map from them into new colors. Now in this case, I've chosen a couple of colors, so I'm going to bring those in at the top. These are going to be tailwind colors, so I'm just going to bring in the whole palette with a star. And all we're doing here is creating a vec of these 4 item arrays that represent a color for each vertex. So this is called vertex coloring or vertex colors. We'll talk about what we're actually doing to determine the colors in a second, but we're collecting that into this vec, and then we're taking that vec of colors, vec of arrays, and inserting it as the attribute color, which is the vertex colors. With that in place, we immediately start seeing vastly different results from what we saw earlier. Right, this actually starts to look a little bit like landscape. We actually have some peaks. Those peaks are snow-capped, if you will. And then we have some locations here that are kind of going into the negative. That's because I used a slightly different kind of calculation. But really, all of this coloring is arbitrary. If you think about this as being a number from -1 to 1, right? Perlin noise gives us -1 to 1. Then at the very bottom, you're going to want to make, you know, everything below 0.2 just maybe black. Everything above 0.8, maybe that's the peak of your mountain. Everything above, I don't know, 0.4 or something like that can start to grow into a mountain with this brownish color. So we have our wireframes in here, and that makes it very, very much easier to determine exactly what's going on with these colors. So if you can see my cursor here, this is the vertex or the triangle in which the transition happens from brown to green, right? That's because this is a brown vertex, this is a brown vertex, this is a brown vertex, and this is a green vertex. So we end up with this almost automatic fading from brown to green, and then we get green down here. And that's true for pretty much everything here. Now the mountaintops I've chosen to do a little bit differently. You can control a little bit more what this transition looks like. So what we've done here is taken the terrain height, multiplied it by 2, and kind of gone back to the original, if you will. So while the terrain height is going to be -1 to 1 or something like that, here we're going to end up with a value that's like 0 or -1 to 1. So if we debug this G, all of these values look very much more like they are in that range. We've got some 0.7s here, 0.5, some -0.3, 0.2, 0.1. So we end up with something that is effectively -1 to 1 again, based on the value that we set that vertex to. And if we're thinking about that as -1 to 1, then anything that is over 0.8, we are turning into this very bright white color, right? This is far more value than RGB can kind of hold, which kind of gives us that effect that we were talking about. So if we do it more like this, if I don't zoom in too far and I can actually move the camera here, you can start seeing that there's a little bit more of that transition from the white to the brown here. But if I bump that way up, we kind of end up with something that's significantly harsher. So we're creating linear RGBA values here. So 0 to 1. We'll go over what this 20 value has as an effect in a little bit when we talk about bloom. But basically any value over 1 is going to start to give you a little bit more bloom with the default settings. We take that linear RGBA, we turn that into a linear value, and then we turn that into an F32 array, which gives us our F32 4-length array. So this is how you can take effectively anything that is defined as a color in Bevy, whether it's linear RGBA, or it's a tailwind color, or it's the black constant on the color struct, or enum, I guess it is now. You take those all, you put them to linear to the F32 array, and you get that 4-length F32 array. And you can see that I'm just doing something very basic here. If the number is greater than 0.8, it's this really intense white color. If it's greater than 0.3, it starts to turn into like that brown mountainy color. If it's less than 0.8, -0.8 that is, then we're coloring it black, and otherwise it's green. So the default for everything else is that green color. Then we take that, we put that in as the attribute color, and we get this. Now, this is really interesting because now that we have, noise, we can also seed it. So let's seed it for 200 and see what that is. If we just zoom straight out, you can see kind of like there's this big mountain here, maybe a couple of gaps. If I choose something else like 900 and we just zoom straight out, we've got a very different terrain. So you can kind of just dump in seeds and see how this works for you. Now, we don't have the environment map light. We don't have the water. The water would cover these black areas. You can do any number of more interesting things here as well. Nothing is tied to the fact that it needs to work this way. You can define whatever color you want based on whatever values are here or whatever other values you want as well. And you can kind of do whatever you want here. So in this case, what I've done is I've taken the R and the B values, or in this case, because we're iterating over positions, this would be X and Z, whereas G is Y. And for all these green areas, I decided that maybe they were a little bit too flat for me for whatever reason, and I wanted to add some noise to them. So we can take this green color, get it to a linear value, multiply it by a noise value that we gathered. So this is noise, the X and the Z values over 30, so a little bit smoother than you might expect. And then here we add 1 and divide by 2, which gets us a range from 0 to 1. Remember, this noise is from -1 to 1. So if we add 1, then it's 0 to 2. If we divide by 2, then it's 0 to 1. If we divide by 2 again, it's 0 to 5. And if we add 5, then it's 0.5 to 1. So we don't get any black values in our grass. We'll get values that are either 50% to 100% of that value by multiplying it here. And this could be increasingly more gradual, whatever we wanted to do here. Maybe this wouldn't be a noise value. Maybe this would be, maybe instead of pure green, that becomes a mix with yellow. In this case, that would be green to linear plus yellow to linear times F32. This is, I want to mention, not really the correct way, quote unquote, to mix colors. It is just a way, but I'm not going to add any of that noise at all. So I'll turn these back into underscores, and you can play with that however you want, making whatever kinds of terrain that you want. If you do make terrain based on this, show me. Let me know what you make. We will do another video on the water and another video on environment maps, and then maybe we can do some sampling or something like that for placing, trees and things like that. That is what we would need to do to upgrade to 0.15. We can technically do sampling in 0.14, but there's much better support for it in 0.15. So I think that's it for today. I'll push this up both as a branch from what we did in the video exactly, as well as the demo that I showed at the beginning. And if you have any questions, leave them in the comments and we can cover them in follow-up videos. Have a great rest of your day.